right. Well, it is 10:30. I'm going to get started. Are there any questions regarding functions, the stuff that we have been talking about, or the homework assignment? Yep. Go ahead.
Question on the homework assignment.
Yes.
When you're doing quiz, they had a symbol that you're trying to do with all rational numbers, which is like an time. It was a little confusing when I was doing
Hey, go ahead. I know what he's talking about is like they say for all real numbers or for all integers, but the symbol you use was like this I, the letter I, and I haven't seen it before.
Okay. So if the I is written like this, it refers to a set of all integers.
Integers? Okay.
Yeah. So if it is an R, it refers to such a set of all real numbers.
Because I thought Z was.
Z is probably for natural numbers.
I understand.
Sorry?
Z is for
Sorry?
Z is for integers.
Z is for integers?
Yes.
Okay. Yes. But in this comment, I was using the I for integers. Okay. So are there any other questions? Now this one, you're not going to get a grade back, like right away, because there are some questions that are open format. So I will have to grade those, individually. So that's going to take a while because there are 4 questions like that, and then multiply that by the number of students in this class. So that's going to be, it's going to take a little bit of time. Okay. Any other questions related to that? No questions? Okay. Well, if there are no questions about functions, we'll move on, and we are going to finish up how we count numbers in a set. Okay. So in this case, we're not quite done with this yet. Okay. We are kind of halfway through. We talked about this part already. Let me just kind of magnify it a little bit. We talked about the cardinality of all natural numbers is supposed to be aleph, yep. So this is aleph 0. So we basically just define this symbol to mean that it is the cardinality of natural numbers. But this way we have a way to also refer to the cardinality of other sets that have an infinite number of elements, because at least we can now say, okay, if we can find a bijective function, in this case, let me just highlight the portion that we are talking about here. If you can find a bijective function so that you can map another set that also has an infinite number of elements, but if you can find a way to map in a bijective fashion into the set of all integer or all natural numbers, then we can, the name to call this is countably infinite if f is bijective. If it is only injective, it is just called countable. Are there any questions about the two names? When is it only called countable and when it is called countably infinite? No questions about that differentiation? Okay, because one applies to function f being only injective but not surjective. The other one is when it is both injective and surjective, then it is called countably infinite. Okay, now this is kind of interesting. Last time we also talked about this one here, and then after class, there were a few questions, and I recorded a cisp440 supplemental. And thank you for whoever reminded me to upload the recording, because I almost deleted that recording because I thought I got it uploaded already. Let's save some space on my hard drive, and then fortunately I have not deleted the video yet, so now it is on YouTube. But there's a supplemental that you might want to watch because there were only like about 3 people in class at the time, and we talked about it, and then fortunately, I had the recorder on, so if you want to check it out, it's already online. It is cisp440, and it has a supplemental next to it, right here. So it's only about 7 minutes long, but I think it'll be really helpful. If you want to watch it, it'll be helpful because it kind of supplements all the stuff that we talked about last time. All right. So getting back to here, okay, this is what we talked about last time, is a function, a way to map integers in this case to natural numbers. And because this particular function or this way of mapping is both injective and surjective, that means the set of all integers is a countably infinite set. Okay, because we have a way to use a bijective function to map integers into natural numbers. Are there any questions about this mapping? Because this is what we talked about last time. No questions? Okay. If you want to use a mental picture to remember how this is mapped, it's kind of like folding integers into natural numbers. So what you do is you stretch out the natural numbers, and then you fold integers back onto the one side, and then we use even numbers for non-negative numbers, and then we use odd numbers for negative numbers, or numbers that were negative in the integer domain, but they will be mapped to odd numbers into the codomain. Any questions about this mapping? No questions? Okay. So this one doesn't seem very challenging, but we'll take a look at another one that seems a little bit more challenging, and that has to do with rational numbers. Does anyone still remember what rational numbers are? Okay, can someone give me a brief description of what is a rational number? Come on, you guys should know this. Yep, go ahead.
Infinite decimal numbers up to the decimal place.
Well, not exactly, but you're close, okay? So what a rational number is basically a value that can be written as a fraction with an integer as the numerator and with another integer as the denominator. Now 1, obviously, is going to be a rational number because you write 1 as 1 over 1, okay? But a lot of numbers fall into this category, and it doesn't seem like there would be a way to map all rational numbers into just natural numbers in a one-to-one fashion. Okay, so we'll take a look at a particular way to map numbers and say, well, as it turns out, we have a way to do this too. Okay, are there any questions about this? No. Okay. So the first thing we'll go over is this part here. So we'll first find a function f so that we can map the Cartesian product of natural number and natural number to natural number that is injective. Okay, so this is not going to be, I'm not going to prove that it is surjective, but we know that it is at least injective. In other words, if you give me a tuple of two numbers, okay, and each component can be a natural number, can be any natural number, so we just call this x, y here. I will give you a way to map it to a unique number on the other side. Let's call it z, that is a natural number. So x is a natural number, y is a natural number. This is a mapping to z, which is also a natural number. And this function, this mapping, is injective, at least. Okay, so that's what we want to do. All right, so this problem is a little bit more challenging compared to mapping all integers to natural number, because the other one is basically still linear. It is just linear, but it extends out on both sides, as opposed to this one, which is two-dimensional. So we want to map something that is quote-unquote two-dimensional into one dimension and still want it to be injective. All right? Any questions about what we are trying to do? No questions? Okay. So the way we do this is it's actually easy to draw this. In the notes, I describe it, but it's easy to draw it. So what you want to do is to kind of imagine that you have two axes, x, y. So this is our x-axis here, and this is our y-axis here. So the way you do it is you traverse the pixels, quote-unquote pixels, because we are not dealing with real numbers. We're dealing with actual just integers or natural numbers in this case. So we are actually looking at this as individual pixels. This pixel is going to get assigned a natural number of 0. Okay? And then what we do is we are going to sweep diagonally. So we'll make this one a 1, this one a 2. Okay? Then we'll make this one a 3, 4, 5, 6, 7, 8, 9, and so on. In other words, we are traversing in a diagonal fashion. When we hit the one end of the diagonal line, we'll basically rewind it to start on the next diagonal line. So this way, you can see, how, using this particular way, I can basically span the entire two-dimensional space of all two tuples where we have natural numbers of in both components. Is that working out okay so far? Okay. So if you want to, you can kind of fill this in a little bit more. We got 10, 11, 12, 13, 14, and so on. So are there any questions about this particular way of mapping a two-tuple of natural numbers to just one single natural number? So here's the second question. We know this is injective. Okay? The reason why we know this is injective is because each pixel has a unique number. Okay? That makes it injective. So now the reverse question is it also surjective? If I pick a natural number, can I use this way to find out its quote-unquote coordinate in the 2D space? And the answer is yes. Okay? So that means this way of mapping is actually bijective. That also means if you look at the Cartesian product of natural number and natural number, this mapping is countably infinite, or infinite counting. What is the name of that? I just want to be sure. Countably infinite, right here. It's countably infinite because it's bijective. All right. Okay, now that we know this is countably infinite because the mapping is bijective, what about 3? What about a 3-tuple of natural numbers? What do you think? In other words, we are now thinking about this. See, we are getting more and more ambitious, right? What about this? And can I map it to natural numbers in a at least injective way? What do you think? But how would you do it? Okay, you extend this approach. Go ahead.
Could you use another axis?
You can use another axis. Exactly. You use the z-axis. So it's a little bit harder to draw it because now we are trying to project a 3D thing onto a 2D board here. But you use the same approach. Okay. So the one at the corner is still a 0, and then you do the traversal. It's kind of like a two-dimensional sweep this time. It's not a one-dimensional sweep, but it's the same thing. The first plane, quote-unquote plane, is going to be this space here. And then you move on to the next plane, and then you move on to the next plane, and so on. So extending this approach using this particular way, you can actually map any fixed number of Cartesian products of the natural number into all natural numbers, which is kind of cool if you think about it. Any questions about this? Yes? No? Not a question? There's no problems with this? Okay, at least understand the two-dimensional one, okay, because this one is easy to visualize. The 3D one is a little bit harder to visualize, but basically you have a three-dimensional space, and then you are extending it out using a triangle plane, and you're just extending the triangle plane, with each step. Go ahead.
What about mapping the negatives? Is it similar?
Mapping the negative is easy because all you need is to extend it out with a 0, 1 set here, and a 0 can mean negative, and a 1 can mean non-negative. So it's we also know that we have a way to map all integers into natural numbers already, so we can use that approach as well. Okay, any other questions?
Do you have a real-life example of this? Something that we use in programming?
Something that we use in programming. I don't think this is used in a daily programming basis, but if you think about it, there are some relationship. It's not a direct relationship with this one. If you have an n-dimensional array in programming, there's always a way to look at it as a single linear one-dimensional array. So that sort of is kind of what we're trying to do here. But in programming, we never really have to deal with an infinite or a set of infinite numbers or a set of infinite elements. Because as much as we want to say, hey, this is I is an integer, it really is not an integer. Because it can only go from a certain value to a certain value. It is more of a modulo, nature than really just an integer. And that's why in theory, there are some things that we can do in math that we cannot do in programming. Because in programming, we only have a fixed number of bits in memory, and you cannot represent a set that has an infinite number of elements. So that's a good question, but the reason why sometimes there's no direct mapping from theory back to programming is because of that constraint of programming. But it's still kind of interesting to see how we can, use integers only or natural numbers only to represent something that is actually, by its very nature, two-dimensional. And we can extend that approach to basically fold any, as long as it is pixel-based, in other words, as long as it's discrete and not a real number, we can fold all of that into a natural number line. And it's a bijective function also. So that's really helpful in solving a lot of problems. All right. Well, getting back to rational numbers. Remember what a rational number is? A rational number is something that can be represented by an integer as the numerator, as an integer as the denominator. The sign is kind of like an extra thing. We can deal with the sign later. But if we have a way to map this into natural numbers, don't you think rational numbers is really just kind of a subset of something like this? It really is. Okay, it's a subset. It's not exactly like this because we don't have 0 divided by 0 as a rational number. Okay, so that's why it is only a subset. And also, 3 over 3 is not really unique. It really is the same thing as 1 over 1, and that's why when we map rational numbers into natural numbers, it is only injective but not surjective. Are there any questions about this mapping? No questions? All right. And I think that is the end of the discussion of countability of sets. Basically, at this point, we are only interested in can we fold something into natural numbers, okay? And anything that can fold into natural numbers in a bijective way is we say that it has a cardinality of aleph 0. That's just a way to call that cardinality. All right. Yeah,
What
go
is
ahead.
Z again?
Sorry?
Is Z a set?
Z. No, this is really just that. I should have said it this way.
Oh, okay.
So we are picking, a particular example. X is a natural number, Y is a natural number. Can I find a way to map X, Y to Z, which is also a natural number? And the answer is yes, because we can use this little way to traverse a 2D space in a particular way, so that every single pixel in this particular 2D space can map to a natural number in a bijective way. Yep, go ahead.
When we map from a rational number to a natural number, because the function is only injective, and can we say that the cardinality is actually less than the cardinality of n?
Less than aleph 0? I suppose we can say that. I don't quote me on that, okay? I only know that if it's bijective, then you can use aleph 0 as the symbol for the cardinality. But whether you can compare and say this is less than the other cardinality, I'm not 100% sure about that. Yep. Question?
We kind of had questions about the homework.
Mm-hmm.
So, how come like f of x equals 2x is, sorry, let me just say, it's injective but not surjective.
Okay.
What x plus x is.
Okay, so here's a question from the homework assignment itself. And I think the question is f of x is 2x. Okay, we'll read the rest of the question. What is I always indicate what is the domain and the codomain.
Oh, this is across integers.
Across integers.
Yeah.
So across integers, it is different from across real numbers. Because across integers, for every element in the domain, there's always something in the codomain to map to, which makes it, and it's always unique. So that makes it injective. But it is not surjective because all odd numbers in the codomain are not mapped to. That's why it is injective, but not surjective.
Oh, I get it. I was just asking.
Okay.
Because I got asked by a couple people.
Oh, okay. But on the other hand, if I use real numbers as both the domain and the codomain, then it is injective and also surjective, because for every element in the codomain, you just have to divide it by 2, then you get back to an element in the domain. So that's why, for those questions, for each one, I have to clearly indicate what is the domain and what is the codomain.
So just to be clear, across integers. So because while in the codomain everything, well, items or elements in the codomain uniquely map to elements in the domain, it makes it injective. But not every element in the codomain maps to an element in the domain, so that doesn't make it surjective.
Correct.
Okay.
The other way to say that is, if 2 different elements in the domain always map to 2 different elements in the codomain, but certain elements in the codomain are not mapped at all.
Right.
Yep. Go ahead.
Did you say that function was injective and not surjective?
If we're only considering integers, then it is injective, but it is not surjective.
But how's injective? Like, wouldn't the -1 be
Negative 1 maps to -2.
Oh wait, no, never mind.
In order for the
that function,
injective,
it maps to every other element. And
Right.
all the elements are unique in their mapping.
Yes.
It's, with injective functions, you don't have to have every element in the codomain mapped.
Yes.
It just has to be uniquely mapped.
correct.
Whereas it's with surjective, every element in the codomain has to be mapped to something in the
That is
domain.
correct.
Oh, sorry, I was looking at 2x squared, x squared. Sorry, I was.
Yeah, x squared is a different story. Okay, so let's go back to the homework assignment. So if you look at f of x is x squared, and what is the domain and codomain in this case? Do I use real numbers in both cases?
It has to be all positive.
Well, yeah, if I use, this to basically say, real numbers for the domain and real numbers for the codomain, then it is injective. Well, it is not injective either, because, 1 and -1, they both map to the same element on the other side. But it's also not surjective because negative numbers on this side are not mapped at all. So it is neither injective nor surjective for squares.
But if you had a restricted domain, it'd be totally different.
Correct. If I restrict the domain, then there's a different story. Right.
And
If I restrict the domain,
Then it
or
will only be
restrict the
surjective.
codomain, it's
Yeah.
the codomain that really matters.
Yeah.
If I restrict the codomain to be all real numbers that are non-negative, then the story changes.
then it's surjective.
Then it is surjective, but it is still not injective.
You get that over here.
Yeah.
Okay, is that okay so far? You guys, yep, go ahead.
Just a question about the text that you use for the typing in the formulas and stuff. Is there any way that we can get a handout or some other website that we can go look up what we want to use, what command we have to use? Because the stuff that you had in the homework, I copied it the other way and in the math jacks and it didn't work out. So I was pretty much stuck with typing in and stuff.
I think the best way is really just to look at how I type it. Because the other way to do it is to learn LaTeX, the entire thing about LaTeX, which is going to take a little bit of time.
It took me an entire summer.
Took you an entire summer,
Yeah.
so there you go. Yeah, because if you right click on any of my text here, it shows you what it looks like. The trick is you have to use / open parenthesis and / close parenthesis in your HTML editor to indicate this is the beginning and that's the end of the formula.
So if you copy this to math jacks, it's not going to work.
It should work.
Because it didn't.
That,
I tried the formula and it didn't work out, so I had to type stuff.
Okay. Yeah, go ahead.
So instead of like, do you want us to write it out in that kind of format, or are you okay to explain everything in like words?
As long as it is clear to me what you mean, you don't need to use the mathJax format. But the mathJax format, because you'll be using the math symbols that we have been using in class, the chances of you using a symbol that is not what you really should be using would be less. So that's why I kind of want you guys to learn how to use mathJax, but it's not required. But when you have to express, subset of, and stuff like that, it becomes kind of more handy if you can just type in the symbol. Question? No? Okay. Any other questions? Yep.
Sorry, could you explain again why x squared is not surjective?
X squared is not surjective. Well, it depends on the codomain. So are you talking about that the codomain is the set of all real numbers or only non-negative real numbers? Because those two cases are different.
I'm thinking real numbers.
All real numbers, right? And your question is, why is it
Not surjective.
why is it not surjective? Okay. Take any negative number.
-3.
Okay, what is the square root of -3?
9. Oh, it's square root. Oh, sorry.
Because that's what that's how you map it back.
Oh. Okay.
So you cannot find any number in the domain, which is a real number. I'm not including imaginary numbers here. So with real numbers, the square of any real number is non-negative. So that's why you have at least one half of the real numbers unmapped to. And that's why it is not surjective. Because surjective basically means every element in the codomain needs to be mapped.
All right. Thank you.
Okay. But that's why I asked that question, because if I constrain the codomain to be just non-negative real numbers, then it is surjective. So I can always play that trick with the codomain to make it surjective. Yep.
I figured out why if you use the way that you show how to do it, why it doesn't work. So like in LaTeX, there's this thing called a delimiter. Delimiters are what allow the GIF to be generated so that you see the formula. So the delimiter for inline stuff like this is \, open parenthesis, and then the end would be \, close parenthesis. So if you don't use those delimiters, then it won't ever display correctly. Yeah. So if you copy directly from that, you have to put the delimiters in.
Yeah. So is that kind of answering your question? Okay. Right. So any other questions on this particular slide? Are we ready to move on to propositional logic or calculus? Well, I think it's a good time to get started on that topic. We probably won't be done for at least one class and a half. But it's an interesting topic. Okay. All right. So we're going to start with why propositional logic is important and what is a proof in general. All right. So isn't it enough that we think that we know what is true and what is false, and why do we have to bother to prove anything? Some of you here will be so bored with what I'm going to say because you have heard it multiple times, and other of you, because I know some people have never taken the class from me, so it will be the first time you hear that story. When I was working on my doctoral dissertation, which is really just a kind of long paper that you have to write, what I need to work on had a theorem. Okay, so my advisor, which basically quote unquote my boss, when I'm working on my dissertation, said, okay, Tack, this is the problem that I want you to work on, but other people have worked on this problem already, and they got up to this particular point. Okay, so this theorem is established, so you can start your dissertation based on this particular theorem. So I said, okay, cool. I'm not going to redo all the work that has been done before. So I worked on it for maybe 2 months or 3 at the most, and it just didn't seem to me that it was obvious that that theorem has to be true. Okay, so I asked my advisor, and I asked him, okay, are we sure this theorem is proven? Are we sure that this has to be true? And he said, oh yeah, so and so's master's thesis has already proven that this particular theorem is true, and go like, okay, I'll go check it out. So I did. Okay, so I went to the library and checked out the master's thesis, which supposedly has a proof of this particular theorem. So I went to the page that has this theorem introduced, and instead of a mathematical proof with all the symbols that you guys are now familiar with or should be familiar with, there's just one statement saying, obviously this is true. And in math land or computer science land, the word obviously is typically called a famous last word. Because anything that is quote unquote obvious usually is either not obvious or it is wrong. So I went back to my advisor and go like, well, I can see that there's an argument that this is obviously true, but I do not see the actual proof that it is true. So my advisor said, oh, don't waste your time, just move on with your part of the research. I go like, but I don't feel comfortable. So I said, can I have 1 week to work on this so that I can try to find a counterexample to prove the theorem wrong? My advisor said, okay, fine, go ahead. So I did. Okay, I spent a week and I found one counterexample to prove the theorem wrong. So this is the cool part about proving someone wrong is easy because you just need one counterexample. And that's enough, right? That's enough to say there exists one counterexample where this theorem is not true, that the theorem is not true. So I presented my counterexample to my advisor, and what do you think would be his response?
Forget about it. Just keep going on.
Not quite that bad. I can see some people doing it, but not my advisor. He's not that bad. His response was a one-worder. Oh. That was it. That was the entire conversation. So I had to basically go back and basically, work out which part of my dissertation is invalidated because the theorem is not true. And it turned out it wasn't really much. It didn't impact me much. But I went to the computer lab where there were other graduate students, and I told this to one of the master's students at the time. And this guy has been working on his thesis for 2 to 3 years already, okay, which is kind of like overdue already. And I told him about it, and he said, and he just kind of kept it in, and then he said, I'm going to kill blah, 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 my advisor. That's what he said. He didn't do it. He's not that kind of person, but he was fuming because it can potentially invalidate everything that he did for the past 2 or 3 years. Yeah, exactly. That's one of those moments. Yep, exactly. So that's the introduction to what is a proof and why do we need to prove things that that seems to be pretty obvious. Okay, that's why we need to have step-by-step proofs. Okay, so are there any questions about this little story, which is actually real, true? Yep.
If you invalidate his master thesis, does he not get his PhD?
I think there are ways to do it, but I don't think they want to bother to retract his master's degree, because this guy's committee, because every graduate student has a committee. When you have a dissertation or a thesis to write, you have a committee. The composition of his committee is exactly the same as mine. So to invalidate, his thesis would stir up things, that would impact, getting mine done. So I would much rather not to do that. In other words, I had my torpedo tubes flooded, but not, I did not fire the torpedoes. Yep. To tell? Oh, the other guy?
Yeah.
I do not know. That's a good question. Maybe I should poke him once in a while.
What was the theorem? What was the theorem?
It has to do with the theorem has to do with a property of a solution to a stochastic state space search solution.
Wow.
And that's
Yeah, those can be difficult.
Yeah.
Yeah, I think that was my dissertation's title was like a 4-word thing, and if I'm trying to remember what it was. It's stochastic admissible. There we go. Admissible heuristic search. That's it. That's the title of my research.
You got yours from UCD, right?
Yeah.
Search the library UCD.
Yeah, you can go to the library of UC Davis and actually get the printed version of my dissertation. That's way before they put everything online, so you cannot actually find it online. These days, every dissertation is now available online. My dissertation was only about 70 pages when I was done with it, and then and it's all like this. Okay, it's all made out of well, not this slide. This slide is not a good representation of that. I have to go to.
The slide we're going to get to in a couple days.
Yeah, I think this one would be a better one to look at. So my dissertation was basically all kind of like this, like 60, 70 pages of stuff. Kind of all they're all for all there exists element of subset of like that. And then my advisor told me it's like, Jack, you have to write in English. And I go like, but this is more concise. This is actually more concise, and there's no ambiguation. If I miss a step, people can spot it and say, Jack, you miss a step here. Okay, I cannot see how this step and this step connects. And they didn't like it. They didn't like the fact that I'm using all math symbols as much as I could. And then I asked, so if I use a lot of English, where do I put all this stuff? But you can put it into the appendix. But then I'll have a 50-page appendix and a 40-page, actual main content, and it was just kind of funny. I had to. I'm not sure whether I should say it, but I'm gonna do it anyway. I had to fluff it up. I had to get my blender and go like, just fluff it up, and then include like lots of pictures, graphs, diagrams, and stuff like that, to make it a good
pretty.
dissertation. Yeah. Then it was 100 and something pages.
So you wrote a small book.
Well, a master's thesis. Okay, and this guy was in the same lab during the same time that I was there. His master's thesis was 300 plus pages long.
Light reading.
I wouldn't want to read it. Okay, so getting back to the class here. Without the proof, what we think is true may not be the case, and I have just made that point. This happens all the time, even in master's theses and doctoral dissertations. But what is the harm of a theorem or mathematical statement that is actually a false positive? In other words, it really thought to be true, but it really is not the case. What can be so bad about that?
Invalidates everything that was built on top of it.
Yeah, but if you think about it, math is really just, man-made or artificial rules, piling up on top of each other, right? So what is the whole, what is the harm of, a claim that is not true if it's all abstract, right? What do you guys think? Nobody wants to make a statement here?
What happens if everything's based on something that's false?
Exactly.
Then
Okay.
everything that is built on top of the false statement is also false.
Yes.
But how do you know it's false?
So I have one example here that has everything to do with what is considered hot today, popular, or what is what people talk about in industry a lot. So a conclusion that may state that a particular way to encrypt data is difficult to crack. Okay. In other words, someone can come up with a number and basically say, okay, this encryption technique using existing computation theory and computation technology, it will take 200 years. Okay. Even if Moore's law stays, the same way as it is now, it will still take 200 years to crack the encryption, which is plenty of time. Okay. Encryption is not about not being able to crack. It is just about can you crack it in time for the content to be useful. So in the time of war, okay, if the invasion is scheduled in a few months and it takes 2 years to do the decryption, then the decrypting, is ineffective because it would not be helpful at all to fight a war. Okay, so it is not about whether something cannot be cracked. It really has to do with how long does it take to crack it. But if the conclusion is actually false, okay, the encryption may only take minutes to crack in reality. Okay, now this happens a lot too. Okay, it's not like this is completely just something that I made up. DVD encryption. Okay, do you guys still remember? DVDs are supposed to be encrypted.
Yeah.
And how long did it take someone to decrypt it?
A couple months.
It was less than that.
Well, you're talking about like the first available decryptor so you can rip DVD.
Well, no, I'm talking about the first program that at least show in theory DVDs are easy to crack.
Oh yeah,
That was pretty quick. Okay,
VLC.
and that happened because the movie industry, the MPAA, probably did not spend enough money to pay someone to actually prove that their encryption will take actually this long to crack. They didn't care either. All right, so getting back to this part here, what exactly is a proof? A proof is, a logic system starts with axioms. An axiom is a simple statement that is assumed to be true, and we do not question why it is true. Okay, so those are the axioms. Now, when we talk about axioms, we also have to talk about symbols and stuff like that, and so it becomes kind of useful to talk about that stuff too. All right, so we look at this thing here and say, what is it? Okay, we normally look at this and say, that's 1, right? We look at this and we say, that's 0, and so on. But these are just symbols, okay? In other words, it really is a way for us to communicate with other people. By itself, it's meaningless, okay? And then we come up with multiplication, right? This is also just a symbol. So why do you think 1 times whatever, let's call it x here, is x? Why is 1 the identity of multiplication? It's an axiom, okay? What about a plus b is b plus a? Why is addition commutative? It's an axiom, okay? So all of these things are axioms because the axioms also match reality, okay? Because when you want to add the quantity 4 to the quantity of 7, if you do it in the reverse way and you add the quantity of 7 to 4, it ends up to be the same, actual quantity. That's why we have all these axioms, okay? So the axioms at some point has to match reality, has to match the way we use those particular symbols. But once we have the axioms, then we have a logic system that can also perform, transformations where one statement can be inferred by other statements, okay? When we say inferred, it simply means if the first set of statements are true, then the conclusion also has to be true. That's inference. A proof is basically just a step-by-step sequence to link axioms. You have to go all the way to the axioms and statements that are true without, they cannot be proven, okay? And statements using the transformation rules until the conclusion itself is reached. So there's something that we want to show to be true, but we have to start with stuff that is actually given to us to be true, that are not questionable. So if you can associate, or if you can link all the axioms and statements all the way to the conclusion using only the known transformation rules, then you have a proof, step by step, that the conclusion is in fact true. In a way, a proof is not really creating anything new, because the world has an infinite number of statements that are true, and they're all connected by axioms and these transformation rules. So a proof is more like a discovery, okay? It's more like finding a path from the axioms and the known truths and going through transformations to get to what we want to go. Are we doing okay so far with this? Okay, so we are not actually making up anything new. We are actually discovering, something that is already there and finding out how to get there. Okay. So that's why I said right here, a proof is more like the discovery of steps leading to the conclusion, but it's not actually creating a new conclusion. The conclusion has always been there because of the axioms and the transformation rules. Yep.
So you're in the boat that thinks that math is discovered?
I think math is discovery, but sometimes you have, the creative element of math as well, which is to create a whole new system, a whole new formal system in order to model something that could not be modeled by existing formal systems.
So that would be like creating transformation rules?
Like Boolean Algebra. Okay. Now we take Boolean Algebra for granted. It's like, oh, we know all this stuff, right? A or B is B or A. We have De Morgan's law. We have all this stuff here. So by itself, Boolean Algebra is a formal system where you have the axioms, you have the transformation rules, and then you can use it to prove a whole bunch of stuff, right? But before Boolean logic, or before Boole, B-O-O-L-E, the guy who came up with this algebra, formalized the whole system, it's kind of like wishy-washy. People think that, well, I have a pretty good idea this is true, but how do I prove that this is true? But the formal system was not there yet. And as a result, you don't have a formal way to prove something is right, or something is true. Same thing with calculus. So if you look at the history of all major branches of mathematics, you will find the need to create that branch of mathematics. And the creation of a branch of mathematics, a formal system, is actually creativity. It's not really just say, oh, okay, we'll follow the rules. Okay, we are making up the rules. But the rules are not just made up in thin air. It is actually made up to model something that people want to model and say, okay, we want to be able to do this. Okay, but existing math formal systems cannot do it. So how do we make a new system to do it? And for that matter, it's also interesting to see how sometimes math goes ahead of physics and other natural sciences, where there are branches of math that are completely abstract and they have no application whatsoever today. But years later, when physicists or chemists start to realize or start to discover things that they cannot explain using existing math, sometimes those math branches that we thought is completely abstract and useless and pointless suddenly becomes applicable. So there are cases where mathematicians are just way ahead of physical discovery because we don't have instruments yet to find out, oh, you know what, these subatomic atom things actually behave in this particular way. That's a good question. All right, so we are moving on to revisiting basic logical operators. So there should be nothing really new here. I'm just kind of looking at things from a slightly different perspective. Okay. So in this case, I'm going to, for this entire chapter, I'm going to use 0 to mean false and 1 to mean true. Okay, because instead of using T and F, I'm just using zeros and ones. So with this, I can now rewrite conjunction as a function. Okay, I can rewrite it as a function. As a function, what is it mapping to what? What is the domain? The domain of conjunction is a two tuple, and each element of the two tuple is either a 0 or 1, or if you prefer, true or false. What is the codomain? What does it map these things to? Well, it just maps it to either true or false. Okay, this is one way to look at conjunction, is to look at it as a function. Are there any questions about this way of looking at conjunction, or otherwise known as AND in normal conversation, or AND in C++ program? Any questions about this way of looking at things? No? Okay. If there are no questions about this, we'll take a look at the actual definition of conjunction. So this is the actual definition of conjunction, because it is mapping false, false to false. is mapping false true to false, it is mapping true false to false, and it is mapping true true to true. And that's nothing new, right? It's just a different way of looking at the conjunction operator. Instead of looking at it as an operator, now we are just looking at it as a function. And we can do the same thing with disjunction. So disjunction is kind of the same thing. The domain is still the set of all two tuples of zeros and ones, and then the codomain is just 0 and 1. And this is the definition. The only difference is 0, 1 maps to a 1, 1, 0 maps to a 1, and that's the only difference from a conjunction. Negation can also be seen as a function, but this time it is not mapping a two tuple to true false. It is just mapping true false to true false. It's mapping false to true, and it's mapping true to false. So are there any questions about the way we look at logical operators as functions? No questions about this? Okay. Just a new way of looking at things. Okay, there's the meaning of conjunction and disjunction and negation do not change. It's just a new way of looking at it. All right. So from these basic logical operators, we'll also define a new one. I think this is not new. I think we have seen this before. It's called implication. Not A or B is also known as A implies B. That's just the way it is. Okay. And the good thing about Boolean logic is you can always define a function using a truth table. Okay, there's no, you cannot do that with integers easily, but you can do that with Boolean values. So as a result, if this is just not A or B, then we can define implication. And you can see that in this class, when I use implication, it's always with 2 bars instead of 1, because with 1 bar, it is a symbol used in function mapping, and I don't want to confuse people of using the same symbol to mean implication. So implication is always using double bar in this class. It is mapping a 2 tuple of zeros and ones to just 0 and 1. And in this case, this is nothing new. False implies false is true. False implies true is true. True implies false is the only time the implication itself is false. True implies true is true. And this is not something new. We have seen this already. But I just want to double check and make sure that everybody is comfortable with it. Yep?
Why would true implies false be the only one that is false?
Because you get your refund.
So
remember the example, where you pay me some money and then I tell you a wisdom of truth, which is in the form of an implication, and you can get your money back when you can prove what I said is not true. Okay? So that means if I say, I'll use today as an example. Okay? If it's a sunny day, you're gonna flunk the class. It is pretty sunny today, and you're not flunking this class, so you're going to get your money back.
Okay.
Right?
Okay. I see, okay.
But that's the easy part to understand about implication. Most people are hanging up on the first 2 cases, where it is not a sunny day, it's a cloudy day. Okay? So on a cloudy day, you're not going to get your refund back in any case, because you cannot prove me wrong at all. So what I claim to be true is remaining to be true unless it is proven to be wrong. So on a cloudy day, there's no way to prove what I said is wrong. Is that making any sense?
The burden of proof is on me.
Right?
The burden of proof is on me.
That's the way the logic system is set up when you're dealing with implication. And then there's another one, it's called equivalent to. So when you look at the double-sided version of the implication, it's called equivalent to. Now equivalent to can also be defined like this. It means A implies B and B implies A. But the consequence of being the conjunction of A implies B and B implies A is this. Okay? False is equivalent to false is true. true is equivalent to true is true, but the other two cases are false. It's the same thing as saying, if and only if it is a sunny day, you will flunk a class. Okay? It's the same thing as saying that. Probably should not say that too many times. It's kind of demoralizing. I'll pick something else next time. Something like, if and only if you drink Mountain Dew, you will throw up, or something like that. Are there any questions about the operators? Okay, we have talked about conjunction, disjunction, negation, implication, and is equivalent to. Is that part all okay? All right. So now we are getting into the meat of propositional calculus. Now the word calculus is not what you think what calculus is, because I know many of you, if not all, are now taking or have taken calculus 1, 2, and 3, and so on. This calculus has nothing to do with the calculus that you're dealing with, which has to do with like the area under the curve, the area of an object and stuff like that. Calculus as a word is not always implying what it is about. It is simply saying a formal system to deal with a particular type of problem in mathematics. That's basically what calculus is. So propositional calculus is a mathematical system, is a formal mathematical system that deals with, say, propositions. And it's rather abstract because the system is designed to work with a variety of topics. In this class, we're only dealing with logic. So in the end, we're only going to deal with propositional logic. When we describe a propositional calculus system, we know that as a 4-tuple thing, okay? And we'll explain each component. The 4-tuple thing is, okay, lambda here is referring to the calculus itself. Alpha, omega, zeta, and iota are different components that you will need to specify when you deal with a particular propositional system. Okay? And I'll give you, plenty of examples of what these things are. Okay, so we'll start with alpha. Alpha is a set of symbols to be used in a system, and this set includes the following. It includes constants. Okay, I'm skipping the word propositional because it is there, with all the terms anyway. So I'm just going to focus in on constant here. So a constant is basically a symbol that has a value that it represents, but that association cannot change. Okay, yep, go ahead.
Pi.
Pi is in mathematics, in other branches of mathematics, pi is definitely a constant because it is representing a quantity and that association does not change. Okay, so very good. That is definitely one of the cases. This is a constant, right? When you look at this particular symbol, we associate this symbol with the quantity of 1. Okay, and that association does not change. So are there any questions about what is considered a constant or a symbol that is representing a constant? It's just that the association between the symbol and what it represents does not change. Okay. So next we have variables, and because you're all in the computer science program, we all know what a variable is. So a variable basically means a symbol can be associated with any propositional constants. In other words, at one point it can be associated with one particular constant, and you can change it later on, and it can be associated with something else. So the association is not fixed. It can change. Is that okay so far with variables? Okay. The next one is a little bit harder to explain. What is a schemata? Okay, a schemata has to do with something that we will have to talk about. There's a little bit of circular definition here, so we'll have to kind of deal with this a little bit. A schemata is basically a symbol that can associate with what we call a well-formed formula. It is WFF, not WTF. Okay, I know what you guys are seeing, okay, what your mind is telling you, but it is actually WFF for well-formed formula. Okay, and we'll talk about that later on. Okay, so basically we have we're defining the alphabet of a particular system. We have 0 and 1 to represent false and true, and then for variables, we typically use P, Q, R, S, the English alphabet, lowercase. And then for schemata, we use Greek symbols, typically lowercase psi. Okay. Psi is this one. We also use phi, which is this one, and sometimes we also use rho, which is this one here. Okay, so those are the Greek symbols that we use to represent schemata. So each one of these is going to be associated with a schemata. And a schemata is basically just a well-formed formula. So we'll deal with well-formed formula a little bit later, because before we can define what is a well-formed formula, we have to talk about the omega set. The omega set is a set of connectives, okay, which is a super-duper fancy word for operators, okay? So otherwise known as operators. A connective has a certain number of parameters, and inside the omega set, sometimes, okay, not all the time, sometimes people want to differentiate into subsets. So omega n is basically a subset of omega, and it has connectives that require n parameters. Okay, it's just a formality. Okay, in this class, this is actually not very important to us. So when you look at logic systems, okay, omega 2, which means all connectives that require two things to operate, would be conjunction, disjunction, implication, and is equivalent to. Those are the things that we have talked about so far in this class.
What is the max omega n then, considering all the logical operators in existence?
You can invent your own connectives.
Can you invent your own?
Sorry?
So you can actually invent new operators?
If you want to, if you want to extend what your logic system can deal with, you can invent your own operators.
But you'd have to define them within.
Then you'll have to define that operator. Yes. Yep. So that means if Tash wants to define his own operator, he can do something like this. Okay. This is the symbol of my operator, and it will take 4 things. Okay. And I just have to define, what is the mapping of this operator. Okay. Then this will become. So in this case, because it takes 4 things, so that means this operator as a connective is going to be an element of omega 4, because omega 4 with a subscript 4 means it is a set of all connectives that require 4 parameters. Now conjunction, on the other hand, only needs 2 things, right? Now by convention, it is a infix operator, but you can always kind of look at it as just a function as well, with 2 parameters. Is that okay? Okay. So that means conjunction as a connective is an element of omega 2 because it has 2 things. Okay, it requires 2 parameters. We only have one that is in omega 1, and that's negation. So negation is an element of omega 1 because it only needs 1 parameter. Are we doing okay so far with what is the omega set? So the bottom line is, as the name implies, a connective is used to connect things. So we'll talk about what things are we really connecting. So here is the section on well-formed formula. Okay. Now well-formed formula is if you look at the alpha set, it is a set of limited elements, at least when we're dealing with propositional logic. Okay, we're just going to say, okay, we'll use these 2 for true and false. We'll use this bunch for variables, and then we'll use these for schemata. When you look at omega, it is also a set of fixed number of elements. Okay, so we have conjunction, disjunction, implication, is equivalent to, and negation. So typically 5 elements in omega is enough for us to deal with the logic system. But when you look at well-formed formulae, it is a really big set. Now, the reason why this is a really big set is the way it is defined. Each element from the set A, which is the alpha set, is by itself a well-formed formula. Okay, that's the ground base, or this is the base of how we build things. So this means a constant, a variable, or a schemata is by itself a well-formed formula. Okay, this part is not hard. Okay, we get that one. But on the other hand, if you use a connective from the omega set, anything that you can make out of a connective is also a schemata. So what this is really saying is for all I that is between 1 and n, and we want to claim that this is phi, so phi subscript I is a well-formed formula, then and omega itself is a symbol or an element in omega n, then this is also a well-formed formula. All it really means is you can use connectives to make big well-formed formula from small well-formed formulae. Is that okay? Kind of? Now, it really is just a fancy way to say that you can make big expressions out of small expressions and operators. And we do it all the time in programming. Okay? Are we doing okay so far? Because I just want you guys to kind of see how we look at it from the abstract perspective, and we have to deal with all these Greek symbols and whatnot, and what it really just means. Okay? It just means that you can make big expressions out of smaller expressions using operators. Are we doing okay so far with what is a well-formed formula? Is that okay? All right. So getting back to schemata, okay, getting back to here. So what this means is every time if you want to refer to not limited to just a constant and not only limited to a single variable, if you want to refer to an entire expression, if you want to refer to an entire expression, you will have to use the Greek symbols. You have to use psi, phi, or rho in general. Okay, you can add additional ones if you want to, but these are the three that people typically make use of. Yep.
What would be an example of not a well-formed formula?
Anything that is not, that you cannot construct out of the recursive definition of the well-formed formula.
So would it not work at all? Or?
I can give you a not well-formed formula using only symbols that we have talked about. Okay. That's not well-formed because it needs something on both sides. Okay. Or something like this, we can have P, and it's not well-formed because negation only takes one parameter, and this is not well-formed. So is that going to answer your question? Okay. or something even this. They're not connected using a connective, so it's not well-formed either. All right. So you can basically see at this point, okay, just stopping with well-formed formula, given a limited set of alpha, okay, alpha that has a limited number of elements, given omega, which also has a limited number of elements, we have an infinite number of well-formed formulae because of that. Is that making any sense? Because it is a recursive definition. You can always make something that is bigger and bigger and bigger and bigger out of the connectives. Okay, so that's why the connectives, the stuff that is in the omega set, is really important because that is what makes this system dynamic. Okay, you can create more and more well-formed formula. But all of this well-formed formula is completely meaningless. Okay, it is syntactically correct. So when you look at the system up to this point, it basically says, oh yeah, this is a well-formed formula. Okay, that's cool. This is a well-formed formula. This is a well-formed formula all by itself. We can say this is a well-formed formula. These are all well-formed formula. But what do they mean? I don't know. Nobody says anything about the meaning of any of these things. Not even this, not even 1 or 0. We just know that these are symbols that we are allowed to use. but there's no meaning. There are no meanings whatsoever associated with the symbol 1, the symbol 0, or any of the connectors. So up to this point, we have the syntax, but we can make completely senseless sentences out of these words because nobody is actually grounding the system to anything that has any particular meaning. Are we doing okay so far? So the truth table of, go ahead, sorry.
I have a question. So that one would be a well-formed formula by itself.
Yes.
But if we were to put like a P next to it, it wouldn't.
That is correct, because if you have two elements from the alpha set, you have to connect those two with a omega 2 element.
So we have to use like the less than or something? Or and?
We only have and, or, not, implies, and is equivalent to. So those are the 5 that we use when we're dealing with a logic system. Less than, greater than, those are useful when you're dealing with actual numbers, but since we're not dealing with numbers, they're not actually used.
So those aren't the omega 2 operators though?
They're not in the omega 2. The propositional logic system can only deal with statements. Okay, so P, Q, R, and so on, they can, each one can represent a particular statement, but it cannot, we don't have the ability to indicate, A is less than B. That is not within the ability of propositional logic. But it does lay out the groundwork to deal with stuff like that later on. So at this point, I'm just giving you. I just talked about this, so this is the right time to do it. So basically, we have alpha being, this is phi, this is psi, this is rho, this is just regular P, Q, R, S, T, U, and this is 0, and this is 1. Okay, so these are the symbols that we can use. This is almost like A to Z in the English alphabet. Okay, they form the most elemental components that we can use to express anything. We have omega 1, which is just the negation symbol, with omega 2, which is and, or, implies, and is equivalent to. And I give you a few examples of what is a well-formed formula. So we typically write P and Q as P, P, and then this is called a wedge symbol, Q. But you can also rewrite it like a function like this, okay? Because it's just another way to express the same thing. But there's no meaning up to this point, okay? This is one part of the syntactic aspect of propositional calculus, but nothing has meaning up to this point, because the meaning is associated with the iota set. The iota set is basically the initial point or axioms. So each element of iota is a WFF or a well-formed formula that is true. And we don't question why they're true. They're just known to be true. So at this point, we'll go ahead and introduce these well-formed formulae that are true to begin with. We don't question why these things are true. Okay? So we basically say 1 is true. Okay? We say the negation of 0 is true. So these are all by definition. And then we say the negation of 0 and 0 is true, which is basically saying 0 and 0 is false. Okay? But we have to confirm whatever you express here has to be what is true. You cannot say what is false. Okay? And there's no equal symbol either, so you cannot say blah 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 equals 0. Okay? And we know that 0 and 1 is true, so that means the negation of that is, take it back, 0 and 1 is false, the negation of that is true. We also have 1 and 0 being false, the negation of that is true. 1 and 1 itself is true, so we can just do it by itself, and so on. Okay, so we'll define a whole bunch of terms like this. You can just kind of imagine with all operators or all connectors from omega 2, there'll be 4 entries here. So if we have 4 entries in omega 2, there'll be 16 entries corresponding to those connectors here. And then we have the negation already handled on the other side. So we are basically all set. Okay, so this is how we define. This is how we give meanings to the connectives. Without the iota set, there's no meaning to the operators. Are we still doing okay so far with the components of a propositional calculus systems. Okay, just to recap, we have alpha, which is basically the same thing as the alphabet. Okay, we have omega, which defines all the connectives. Now the connectives are kind of cool because they can nest, they can build up larger and larger and larger well-formed formulae. And then we have iota, which defines the meaning of the most basic operators. But up to this point, we are still lacking something that is really important, and that has to do with the zeta set. Up to this point, we have a very basic language specified. So if you look at it from the perspective of a programming language, we have a language already specified. It's just like the C programming language can be specified by a whole bunch of what we call productions or syntactic rules. Okay, and we have a language completely specified now, along with what each statement is supposed to do. But that's only useful up to a certain point because the computer cannot understand C or C++. The processor only understands what? Machine code, binary code. So the zeta set is kind of like the transformation rules, so that you can go from one form to another form. Kind of, okay, I'm emphasizing on the kind of here. So what we have here is the zeta set is a set of transformation rules. Each one is a rule that basically says it is in the form of this. Okay, this is how each rule will look like. On the left-hand side of that little symbol, it's called a B dash, by the way. If you want to enter this in LaTeX, it's called B dash with a lowercase d. So if you type \B dash, it will give you this little symbol here. Okay? So what it means is, given the premises of these particular well-formed formulae, you can infer this as a conclusion. That's basically what it means. But it's not really quite the same thing as implication. It has a relationship with implication, but not exactly the same thing. This is all syntactic. That's all it is. Okay? So that means we can specify rules. We have a whole bunch of rules that we can see later on, but I'm going to skip a little bit forward just so they can see what one particular rule looks like. So we can pick one that is kind of obvious. Let's pick. I'm trying to pick one that is obvious. These are actually not very obvious. Okay, I'm just going to write one on the whiteboard because I don't want to do these guys with more complicated. Okay, you can have a rule that says this. Okay, so you can have a rule that says P Q. Okay. So this is a kind of trivial transformation rule. It basically says if variable P is true and variable Q is true, then we can infer the P and Q is true, which is kind of trivial, right? I mean, there's nothing to it. But it's a transformation, okay? It does not really look into the meaning of the operator. It basically just says, oh, I'm pattern matching here, okay? If I know this is true and this is true, then syntactically I will create this thing here that is also true. Are we doing okay so far? This is syntactic. It's just pattern matching. Now you also have to remember everything on the other side is a set. Okay, on the left-hand side we have a set of well-formed formulae that are true, and then on the right-hand side we have another well-formed formula that has to be true, but the transformation is completely syntactic. It's pattern matching. Okay, if you can see something on one side, then it will go to the other side. Are we still doing okay so far with this? Okay, I'll give you another example. So we'll say in a particular funny system, okay, so So we'll say psi, that phase, this is phi, okay? And this is the only well-formed formula. Now, obviously, in this case, I have to put this sad phase into omega 2 so that it becomes aconnected. And on the other side, this is a syntactic transformation. Remember, it's a syntactic transformation. There's nothing associated with the mean. So on the other side, I can now say, you know what? This is going to infer this. This can be a syntactic rule. It can be a transformation rule. But then someone is going to ask, okay, now that we know the sad phase and the happy phase are both in omega 2, what do they actually mean? I don't know. I just specified a random rule that says, syntactically speaking, if you see something that appears in this form, it infers that you can write this as a well-formed formula. That is also true. But what exactly is a happy phase? What does it mean? I don't know. What is a sad phase? I don't know. It's just an operator. So it is really just pattern matching. Are we doing okay so far with that part? Okay. This operator or this symbol has no association with the meaning of operators. It is completely syntactic. If you see this, you can mechanically transform that into this. That's all. Are we doing okay so far? So with only this, okay, with the inference mechanism, I can make up senseless and wrong transformation rules, right? I can make up rules that are contrary to the meaning of the actual connectives. So the next question, which we'll address on Thursday, is how do we characterize a propositional calculus system so that it is actually sound and it is complete, okay? In other words, it's balanced, okay? It actually makes sense, okay? Because I can easily make some system that is completely senseless, okay? It doesn't make any sense, so it doesn't serve any actual purpose. So on Thursday, we'll talk about how we characterize a system that actually is useful. Try to read ahead of me before Thursday because this stuff takes some time to soak.